In this video, we're going to look at the end behavior of rational functions. So with a rational function, here's a general rational function, f at x equals p at x over q at x, where p at x and q at x are both polynomial functions. So we want to talk about end behavior. So that means what happens to f at x as x approaches infinity or x approaches minus infinity. So in order to do this, first let's just look at each part. So as x approaches infinity, well, I know p at x is a um, polynomial function, which means p at x, all polynomial functions approach either infinity or minus infinity, and the same would hold for q at x. So we're going to have two functions both approaching infinity or minus infinity. For the sake of simplicity, let's just consider the case that they're both approaching infinity. So you would have f at x approaching something which is approaching infinity. So we could say infinity over infinity. Now this is not something you would normally write. Infinity divided by infinity doesn't technically make sense because these are not numbers. But for the purpose of just discussing it, what does this mean? So remember, what infinity means is a very large number divided by a very large number. So what is a very large number divided by a very large number? And the answer to that question is we don't know. So we don't know what this value is. Sometimes people look at this and say, well, a big number divided by a big number, it's the same thing, so it's going to be equal to 1, right? Anything divided by itself is 1. But remember, infinity just means a big number. It's not a specific big number. So, for example, let's say you had f at x equal, um, let's do a linear function, x plus 1 over a quadratic function, x squared minus 2x plus 1. Let's go plus 4. So if I say x is going to infinity, well, this is a large number. That's the same thing would hold, right? This would go to infinity, and this would go to infinity, but it wouldn't approach 1 because this numerator, if you subbed in an x value, let's say you subbed in 1,000, this would be 1,001. Whereas this would be a much larger number because you'd be squaring 1,000. So while they both be very large numbers, the denominator would be much bigger. So it's not going to divide to 1. So we need to do a little more work to figure out what's happening. And let's actually use this as our first example. So there's actually 3 cases you have to consider. And it all has to do with the degree of the two polynomials. So in this one, remember, it's p at x over q at x. This example will be degree of p at x, so that's the degree of the numerator, will be less than the degree of q at x. So the denominator has a bigger degree. So what's happening? There's a few different ways you can kind of get at this result, but it just requires a little bit algebraic manipulation to see what's going on. What we'll do for this one is I'm going to do a little trick here. I'm going to divide the numerator and denominator by the highest power, or the highest term, the term with the highest power. So divide p at x and q at x by the term with the highest power, which in this case is x squared. And that's allowed. If you divide the top and the bottom of a fraction by the same value, you're not changing the value of the fraction. So I'm going to take x plus 1 and I'll divide each term by x squared. And then I'm going to take the bottom and divide each term by x squared. So I haven't changed the value of this fraction because I'm dividing each term by x squared. And if I simplify that a little bit, notice here I'll have x over x squared, so that'll be 1 over x plus 1 over x squared. I can't simplify that at all. X squared over x squared, that's 1 minus 2 over x plus 4 over x squared. And now I'm going to think about what happens as x goes to infinity, or even minus infinity. We can say plus or minus infinity. So let's think about each term here. What's going to happen to this term? Well, that's a reciprocal function. So we know that as x approaches infinity, a reciprocal function approaches 0, right? Because the denominator is very big, 1 over a very big number is close to 0. This term is going to approach 0. This term is going to approach 0. And this term is going to approach 0. So what you have is the numerator is approaching 0 plus 0, which is 0, over the denominator, which is 1 minus something approaching 0 plus something approaching 0. So that's 1. So this is going to be equal to or approach 0. So as x approaches plus or minus infinity, y, or f at x, is going to approach 0. Okay? And that will happen anytime this is true. Anytime the degree of the bottom is bigger, you're going to have this situation where you're going to end up with a constant on the bottom and 0 on the top. So that's sort of a rule. You could take that as a rule for any time the degree of the numerator is bigger. The second case is if p at x and q at x have the same degree. In this case, I'm just going to keep things simple, and I'm going to go a linear function over a linear function. So let's say f at x equals ax plus b. I'm going to use a general terms here. And then cx plus d. So a, b, c, and d. You could substitute numbers in here. But I'm going to do the same sort of thing, and we think I need to do the same kind of algebraic trick. Divide by the highest, the term with the highest power, which in this case would be both polynomials have an x as their highest power. So we'll divide by x, both p and q. There's no e in both. Both p at x and q at x. So I would have ax over x plus b over x, cx over x plus d over x. So b out b over x, that's going to go to 0, right? A constant over x, x becomes very large, it approaches 0. Same thing as d over x. Both of these are reciprocal functions. And then these ones, the x's will cancel out. So you're going to have a plus b over x and c plus d over x. Both these things go to 0. And then a and c are constant. So you're going to get a over c. So that's what it's going to end up approaching, right? As x approaches infinity or minus infinity, y will approach a over c. But what is a over c? A over c is just the leading coefficients of, in this case, x, but that would be whatever you divide by, whatever that highest power is. So therefore the end behavior, you'll have y approaching the quotient of the leading coefficient. So leading coefficient of p at x divided by the leading coefficient of q at x. Okay. And then the third case that we haven't considered is if q at x has higher degree than p at x. So you could consider an example. Let's do an example here. Oh, sorry, we did that one. So q at x has a lower degree. So let's go with a quadratic on the top, x squared minus 5 over a linear on the bottom, x plus 1. So we'll do the same thing, but this time we'll divide by x squared, because x squared is your highest term. So we would have x squared over x squared minus 5 over x squared, x over x squared plus 1 over x squared. So I divided each term by x squared. Reduce. I'm going to get 1 minus 5 over x squared. And then 1 over x plus 1 over x squared. So as x goes to plus or minus infinity, this term here is going to 0. This term here is going to 0. And this term here is going to 0. So you've got 1 divided by something approaching 0. Not 1 divided by 0, but 1 approaching something divided by 0. So 1 over something very small. Well, 1 divided by something very small would be something very big. How big? Well, the smaller you make the denominator, the bigger that quantity is going to get. So it's actually going to approach as big as you can get, which would be infinity. So as x approaches plus or minus infinity, y goes to infinity. Or minus infinity would depend on the sign. But those are your three cases. So the first case, take it over here. The first case, if the degree of p at x is smaller than the degree of q at x, so like a linear over a quadratic or a cubic, anytime the degree of the bottom is bigger, then y approaches 0. The second case, when the degrees are equal, so a linear over a linear, then you just take your leading coefficients and divide them. And the third case was if the denominator has a lower degree, so like a linear over a quadratic, and then in that case it always approaches infinity. So you can take all three of those as a rule. And that's a rule that you don't have to do this dividing by x every time, dividing by x squared. You can just take it as the rule once you see the degree. And we'll do that in the next video, so we do some examples.